Hi, welcome to my channel. In this lesson, I'm going to discuss about series connection and parallel connection of capacitors, right? So when capacitors are connected in series, there won't be any junction or branches between the capacitors. For example, consider this type of connection is called series connection. Next to next, if the capacitors are connected, that is called series connection of capacitors. So when three capacitors are connected in series to a DC power supply, the EMF of the DC power supply, let it be V naught. This is capacitor C1, the capacitance. This is C2 and this is C3. Say this plate is X1, this is Y1, this is X2, Y2, this is X3 and Y3. Okay, so when capacitors are connected in series, as we learned earlier, the capacitors will start to get charge. What happens? Now, say this plate X1 of the first capacitor, when it gets charge, positive charge, because it's connected to the positive plate, so that means it lost 1, 2, 3, 4, 5 electrons. Just an example I took, it lost 5 electrons. So when it loses 5 electrons, what will happen? These 5 electrons will induce same type of negative charges, same magnitude of negative charges. That means electrons will be attracted on the plate Y towards closer to the positive charges. So outer surface of the plate Y will become positively charged. The same positive charge will stay on the outer surface of the plate Y. Now these positive charges will attract 5 electrons from the plate X2 of the second capacitor. So 5 electrons will flow from plate X2 to the plate Y1. So the plate X2 will become positively charged and that also will carry the same charge, same magnitude of positive charges. So I told the plate X2 is losing 5 electrons. When these electrons reaches the plate Y1, they will neutralize with these positive charges and they will be attracted by these positive charges. So in overall, the plate Y1 consists of 5 negative charges. Now these 5 positive charges will induce 5 negative charges, that is 5 electrons towards closer to them or to the inner surface of the plate Y. So there will be 5 electrons will move to the inner surface of plate Y2 and the outer surface will become same positive 5 charges, consists of positive charges. Again, these positive charges will attract electrons from the plate X3, which is neutral now, but it's going to lose 5 electrons and they will be attracted towards this one. They'll flow. This is a wire. So when 5 electrons flow from uh, plate X3 to the plate Y2, the inner surface of the plate X3 will become positively charged and that will consist of positive 5 charges. So those 5 electrons move to the plate Y2 and they'll neutralize. So effectively, plate Y2 will carry 5 negative charges. Now think about the plate Y3. Now these positive charges, 5 positive charges will induce the same magnitude of, same thing like here, negative charges towards the inner surface of the plate Y3 and outer surface will consist of 5 positive charges. Now from the negative terminal of the negative terminal of the DC power supply, 5 electrons will flow. It will be attracted. These 5 electrons will be attracted by these 5 positive charges, and when they flow, they'll neutralize these 5 positive charges, and effectively the plate Y3 also will get 5 negative charges. So that means when we connect capacitors, whatever the capacitance, can be different capacitance. When we connect capacitors in series, they will be charged to the same magnitude. So that means when capacitors are connected in series, they will carry same magnitude of charge, or they will be charged to the same magnitude. Okay, now they have different capacitance. So according to Q equals CV, they are going to get the same charge. Q equals CV, they are going to get the same charge, but they have different capacitance. So they will have different voltages across them. Maybe the first capacitor, the voltage across it, let it be V1. Across this one will be voltage, let it be V2. And this voltage, let it be V3. But it's a closed circuit. So in this closed circuit, sum of the voltages must be equal to the EMF of the DC power supply. So V1 plus V2 plus V3 will be equal to V0. Instead of V1, I can say, Q equals CV. So Q equals CV. So V equal Q over C. So all are carrying the same charge. So I can say Q over C1 plus Q over C2 plus Q over C3 is equal to V naught. Okay, so in this series connection, our capacitors are connected in series. In this connection, when we charge the system of these capacitors, the total amount of charge flown in the circuit is Q, not 3Q. Careful. The total amount of charge flown in the circuit is Q because same charge. For example, in this diagram, I can say the total amount of charge flown is 5 times 1.6 10 to the power minus 19 coulomb. According to the number of charges I showed on the diagram, the amount of charge flown in the circuit is 5 into 10 to the power minus 19 coulomb electrons, negative charges. So the total charge flown is equal to Q in the circuit. Okay, now I can represent all these three capacitances equivalently by a unique capacitor called equivalent capacitor. So what does it mean, equivalent capacitor means? If I connect that unique capacitor, equivalent capacitor, that means it's equivalent to these three capacitors, those are connected in series. So when I connect this particular capacitor to the same DC power supply, if the charge flown in the circuit, careful, when I connect this particular capacitor C to the same DC power supply V0, if the charge flown in the circuit here also, if it is equal to Q, I said the charges are here Q, all have the same charge Q, then I can call this capacitor is equivalent to all these three capacitors. Okay, so that is capacitance C is called equivalent capacitance of the series connection of these three capacitors. So I can get a relationship between this equivalent capacitance and C1, C2 and C3. So you should understand the meaning of equivalent capacitance. When a capacitor is connected to the same power supply, or when the voltage applied across this capacitor is equal to the total voltage applied across the three capacitors. If the total charge flown in the circuit is equal to charge of any one of these capacitors, then I can call this as the equivalent capacitance of C1, C2, C3 when they are connected in series. Okay, so I define the meaning of equivalent capacitance of series connection. So here the charge is C, the capacitance is charge is Q and the capacitance is C. So here I can write Q equal C V naught because the voltage across this will be V naught. But I know that V naught is equal to Q over C. Q over C is equal to V naught. So I can say this as equation 2, this as equation 1. So here the right side quantity is the same. So the left side quantities should be the same. So equate the left side quantities. So when I equate the left side quantities of these two equations, I will get Q over C1 plus Q over C3, C2 plus Q over C3 is equal to Q over C. All the Q can be cancelled. So 1 over C1 plus 1 over C2 plus 1 over C3 is equal to 1 over C. So the equivalent capacitance, the reciprocal of the equivalent capacitance is equal to sum of the reciprocal of the capacitance. Those are connected in series. So, numerically, the value of C will be smaller than or lower than the lowest capacitance connected in the series. That's numerical reason. So, numerically, the value of C is smaller than the smallest capacitance connected in series. Okay, so what are the relationships between uh, equivalent capacitance and the capacitors? Those are connected in series. Remember that. So when capacitors are connected in series, they will have the same charge. They will carry the same charge, or they will be charged to the same magnitude, but they can have different voltage if they have different capacitance. If they have same capacitance, all three have same capacitance, this voltage will be divided equally. But otherwise, they'll have different voltages, right? And they carry the same charge. So the capacitor which has larger capacitance, Q equals CV, all three carry the same charge. So larger capacitor or capacitor with larger capacitance will have the lowest voltage across it. And also remember that the voltage across the equivalent capacitor is equal to sum of the voltages, addition of the voltages across the series connection. Okay, voltage across the equivalent capacitor. Remember that we need this idea when we are doing calculations. So in series connection, the voltage across the equivalent capacitor is equal to sum, SUM, the addition of the voltages across the capacitors. Those are connected in series. And the charge of the equivalent capacitor will be same as charge of the capacitors. Those are connected in series, so they carry the same magnitude of charge. So what can you say about energy? Energy of this capacitor is exactly same as the sum of the energy stored in the capacitors. Those are connected in series. So I can show that. Now look at here. I can show that the equivalent capacitor means it will carry the same magnitude of energy, that is sum of the energies stored in these three capacitors. So I can say the energy of this capacitor half, energy equal half, I can say half QV or Q squared over 2C, anything I can, right? So I'll say half QV, general equation. So E1, the energy of this one is, E1 is equal to half QV1. Same way, energy of this one is equal to half QV2. This will be half energy of this one, E3 will be equal to half QV3. So the total energy of these three capacitors, I can say E equal half QV1 plus half QV2 plus half QV3. So that will be equal to half Q into V1 plus V2 plus V3. That is going to be half Q. V1 plus V2 plus V3 is equal to V0. Now, when you consider the energy stored in the equivalent capacitance, E0 is equal to half. It will carry the same charge. So Q, the voltage across it is V0. See, both are same. So that means the energy stored in the equivalent capacitor will be equal to sum of the energy stored in the series connection. So you must remember the properties. Same charge as these capacitors, voltage across it will be same as the sum of the voltages of the capacitors connected in series. Energy stored in it will be equal to sum of the energies stored in the capacitors. Those are connected in series. Remember these final conclusion. Okay, so in this diagram, three capacitors are connected across two junctions X and Y. So these three capacitors are directly connected across two junctions X and Y. So that means they are connected in parallel among them. Okay, so the voltage across the capacitor C1 is same as the voltage across the junction XY. Same way, voltage across the capacitor C2 is also same as the voltage across the junction XY. Voltage across the capacitor C3 is also the same as voltage across the junction. But the voltage across the junction is the voltage across the DC power supply. If I say EMF, that will be V0. So all these three capacitors will have the same voltage that is equal to voltage across the junction. Remember that way, voltage across the junction. Don't say that is always. Some students, they memorize the voltage across the capacitors will be same as voltage across the uh, power supply. Okay, in this diagram it is true, but in case if they put another capacitor here, that is not true. Okay, so remember that in when capacitors are connected in parallel, the voltage across the capacitors will be same as or equal to voltage across the junction. But in this particular diagram, voltage across the junction is equal to voltage across the terminals of the DC power supply. EMF is V0. Okay, so according to Q equals CV, since they all have the same voltage across them and they have different capacitance, they will have different charge. That means they will charge to different magnitudes. So all the plates, those are connected to the positive terminal of the DC power supply will carry positive charge, but they will carry different magnitude of charges. Say a capacitor that has larger capacitance will carry larger charge, or that will be stored to larger magnitude of charge. Okay, but all the terminals, all the plates, those are connected to the positive terminal will carry positive charge. So they will have different magnitude of charges. Okay, so they will carry different magnitude of charges. So if I say the charge of the first capacitor is Q1, the charge of the second capacitor is Q2. Okay, so the capacitor which has larger capacitance will carry the large amount of charge, and the capacitor which has lower capacitance will be charged to lower magnitude, right? Okay, so the total amount of charge flown in this circuit, this capacitor gain charge Q1, this capacitor gain charge Q2, this gain charge Q3 means during the charging process, the total charge flown in the circuit is equal to Q1 plus Q2 plus Q3. That is the total amount of charge flown in the circuit. Okay, so I can say Q1 is equal to C1 V, that is V naught. I can say the voltage same, that is the cross junction. Q2 is equal to C2 V naught, and Q3 is equal to C3 V naught. So the total charge flowed in the circuit, if I say Q, that is Q is equal to Q1 plus Q2 plus Q3. So instead of Q1, I can substitute C1 V naught. This is C2 V naught plus C3 V naught. Okay, right. Now I'm going to define the equivalent capacitance. Okay, here also the same meaning. What do you mean by equivalent capacitance means? If I remove all these three capacitors and when I connect a capacitor across XY, if the total charge flowed in the circuit is equal to Q1 plus Q2 plus Q3, that means when I replace these three capacitors by one capacitor, if the charge flown in the circuit is same as the total charge flown in this circuit, then I can say that capacitor is equivalent to parallel connection of these three capacitors. Okay, so when I connect a single capacitor, a unique capacitor, which has capacitance C, across the same power supply, which has EMF V naught, if the charge flown in the circuit Q1 plus Q2 plus Q3, then I can say this capacitance is equivalent to all these three capacitors when they are connected in parallel. That's the meaning of equivalent capacitance. Okay, so the charge flown is Q. Here also the charge flown or the charge carried by the capacitor C should be Q, that is Q1 plus Q2 plus Q3. It's carrying the total charge that flown in this circuit. Okay, so I can say for this capacitor Q equal C V naught. I can say this as an equation 2, this as equation 1. So in this circuit, in these equations, in these two equations, left side quantity is the same. So the right side quantities should be the same. That is C1 V naught plus C2 V naught plus C3 V naught should be equal to C V naught. So all the V naughts will get cancelled. C1 plus C plus C3 is equal to C. That means when the capacitors are connected in parallel, the equivalent capacitance will be equal to sum of the capacitance of the capacitors, those are connected in parallel. Okay, so you must know the properties of parallel connection. So when capacitors are connected in parallel, they will be charged to different charge or they will carry different magnitude of charges, but they will carry or the voltage across them will be the same, which is equal to voltage across the junction. When you compare the parallel connection with equivalent capacitance, the charge of the equivalent capacitor should be same as the sum of the charges of the capacitors, those are connected in parallel, and the voltage across the capacitor, the equivalent capacitor, voltage across the equivalent capacitor will be equal to voltage across the junction XY. We must remember these things when we are answering certain calculations related to parallel connection. Okay, so here also the energy stored in equivalent capacitor is equal to sum of the energy stored in parallel connection. I can show that here. Say here I can say the energy stored in this capacitor, that will be energy stored in it. I can say E1 is equal to half Q1 V naught. E2 is equal to half Q2 V naught, and energy stored in this one, E3 is equal to half Q3 V naught. So the total energy of parallel connection of these capacitors is equal to E1 plus E2 plus E3. So E1, that is half Q1 V naught plus half Q2 V naught plus half Q3 V naught. So that we can take half Q common. It will be V naught. Sorry, I can take V naught common. Yeah, half V naught common if I take. I can say Q1 plus Q2 plus Q3 half V naught. Okay, so half times Q1 plus Q2 plus Q3 V naught. But Q1 plus Q2 plus Q3, if I call it as Q, that's going to be half Q V naught. So that's the total energy of the parallel connection. Okay, when I think about equivalent capacitor, its energy is equal to half Q, I already defined the meaning of Q of the equivalent capacitor. That is the sum of the charges here. So that will be Q1 plus Q2 plus Q3. This Q is equal to Q1 plus Q2 plus Q3. So half Q V naught. You can see both values are the same. So that means equivalent capacitor means the energy stored in it will be equal to sum of the energy of the parallel connection of the capacitors. I hope you understood the meaning of equivalent capacitors. Yeah.